Hi, my name is Ali Shezava from Breacher Digital, and in this video we're going to talk about how noise gets from one point of our PCB to another point of our PCB. There are two main coupling mechanisms that allows noise to get around to where we don't want it. One of them is capacitive coupling and the other one is inductive coupling. So in this video we're going to talk about capacitive coupling, and in the next one we're going to talk about inductive coupling. So as I mentioned earlier, there are two main ways that noise gets from one part of our PCB to another. One of them is inductive coupling and the other one is capacitive coupling. So let us talk about capacitive coupling first. If you imagine we have got a copper plate, we've got another copper plate, and between them we have got an insulator. Let's call that a dielectric. We have made ourselves a capacitor. And of course, this is exactly what happens on our PCB. You have got a top layer, that is copper. You've got a bottom layer, that's probably, let's say, your copper core for your ground perhaps. And you've got this FR4 material in the middle, which is an insulator, which will be the dielectric. So whether we like it or not, we have got some parasitic capacitances on our PCB, and therefore a signal can get from one point to another via this capacitive coupling. Now we know from school level physics that a capacitance of a parallel plate capacitor is epsilon times A divided by D, where this is my capacitance, A is the area of my plate, and D is the distance between them. In case of the standard FR4, for simplicity, let us say that that is 1.6 millimeters. And epsilon is the permittivity of the dielectric material, which for FR4 material we already know. The area here, let us assume for now that we've got 2 centimeter by 2 centimeter. I am just assuming that I've got a MOSFET, I've got a PCB heatsink, and it is that my heatsink size is 2 centimeter by 2 centimeter, and I've got a copper pore underneath. So I have got a parasitic capacitance with this area, this distance between the plates. I know the permittivity, I can work out a capacitance, and this works out to be around 10 picofarads. So I've got 10 picofarads worth of capacitance. Let's see how much noise is going to get through at what frequency. Now, I know that the reactance of the capacitor, that is the resistance that the capacitor puts up against the flow of the current, varies with frequency according to the equation of 1 over 2 pi fc, where f is my frequency. Let us see what happens at different frequencies. Using this equation and using 10 picofarads in there, at 1 hertz, this reactance will be 16 gigaohms. So I'm not too worried, let's say on a power supply, that a 1 hertz signal is going to capacitively couple to somewhere else. Wow, but at 100 kilohertz, this will fall to 160 kiloohms. Still very, very large. So my switching frequency, let's say typically 100 kilohertz, still is going to see a resistance of around 160 kiloohms. So again, at 100 kiloohms, there's not going to be that much capacitive coupling. At 10 megahertz, this will fall to 1.6 kiloohms. So you can see that as the frequency is going up, the amount of resistance that the capacitor is putting up to the flow of current is getting lower, and therefore more noise is going to flow. At 100 megahertz, this falls down to 160 ohms. Now, that's noise, 150 megahertz signal is going to couple, and at 1 gigahertz, it's going to be 16 ohms. So, this is why the high frequency noise gets around a lot easier than low frequencies. And of course, what we're going to do is we're going to go to the lab later and we're going to show you. We've got 2 PCBs, 2 centimeter by 2 centimeter each. We're going to put them on top of each other and change the frequency and see how the noise couples. So I'm here in my lab setup. I've got two little bits of PCB. This is just FR4 material. I've got one here which is 2 centimeter by 2 centimeter. It's a little bit smaller actually. And then I've got another one here. And of course when I put these two on top of each other, I will get exactly what we described. I will get two parallel plates, 2 centimeter by 2 centimeter each, separated by 1.6 millimeters of FR4 insulating material. So let me put these together here, and then I'm going to measure the capacitance of this with my Bode 500, which is right there. So let me just clamp this so that it doesn't move, so we can have consistent measurement. Okay, so I'm going to put that right here. Now, the Bode 500 is measuring the capacitance between these two plates. And you can see here that I have got my impedance of the capacitor is falling, and here I can actually see the capacitance. I have got my cursor set to around 10 megahertz, and you can see that it's in fact 8.19 picofarads, and on the board we calculated to be around 10 picofarads. So we can see that the theory is correct. Next, what I'm going to do is I'm going to show the gain. In other words, when I inject a signal from here, how much of that arrives on the other side, which is going to get picked up. So let me quickly change my setup. I'm going to open my setting, which I prepared earlier. Okay, and now, what is happening now in this screen is that I am sending a signal here. The size of the signal on this cable that I know, and then the size of the signal that is arriving on the receiver is being measured and is being displayed. And you can clearly see that is rising. I've got one cursor at 5 megahertz, and I've got another cursor at 50 megahertz, and the delta between them is 20 dB. So the size of the signal as the frequency goes up at the moment is going with the rate of 20 dB per decade. And you can also see that by the time I get to around 150 megahertz is 0 dBs. That means the size of the signal that I am sending at 150 megahertz is arriving on the other plate at almost exactly the same size. And of course, that is just noise getting through from the top layer of PCB to the bottom layer of PCB. Now what I'm going to do next is I'm going to connect it to the oscilloscope, and we're going to see what happens in time domain. So I'm going to continue injecting this signal, and I'm sweeping it, and you will see that at low frequencies the amount of noise that is arriving, you watch that on the oscilloscope, is small, but as the frequency gets higher, the amount of noise that is coupling gets bigger and bigger and bigger, and of course that is the capacitive coupling that we've discussed in this video. So let me connect that to my oscilloscope. And then I'm going to go to my oscilloscope screen, and there we go. Let me see. Okay, there we go. That's the low frequencies, and you can see that as soon as the frequencies start to go up, the size of the signal that is getting passed to the other plate also goes up. So there we go. That's the end of the video. In the next video, we're going to talk about inductive coupling. Hope you enjoyed this. We run regular workshops on power supply design and EMC. I hope to see you at one of our workshops, and please check out our website.